Hi all, this is the second part of lecture 20 from section 11.1 on sequences. So far we've looked at how to write sequences, how to find terms in a sequence, and then we've looked at the limits and the boundary, the long-term behavior of our sequences. The next thing we want to be able to use to kind of find convergence or divergence is the idea of looking at whether a sequence is increasing or decreasing. So an sequence is increasing if your an term is less than the an plus 1th term for all n greater than or equal to 1, right? So you have to have them increasing. And oops, this is wrong. In decreasing, these should be the other way. Right? This one's bigger than that one. So your an is greater than your next term. Okay? And that's how we show something is increasing or decreasing. So what we want to do is we want to be able to determine which it is, and then we want to show that. So when we take a look at 3 over n plus 5, if I look at the first few terms, this looks like 3 over 6, and then 3 over 7, and then 3 over 8, and so on and so forth. So as we're going, the numerator stays the same, but our denominator is getting bigger, and that means that your number is getting smaller. So this is decreasing over time. So what we want to do is say we want to look at an compared to an plus 1. So we're trying to show that an is greater than an plus 1, because that'll mean that your sequence is decreasing. So an is 3 over n plus 5, right? And we're kind of putting a question mark over that because we're trying to show that. And an plus 1 is 3 over n plus 1 plus 5. Well, really, that is just 3 over n plus 5 compared to 3 over n plus 6. And if you multiply both sides by n plus 5 times n plus 6 to clear my denominators. Now keep in mind that n is a number that's equal to or greater than 1. And so both of those two things are positive. So we're going to keep our inequality sign. And when we do that, we have 3 times n plus 6 being greater than 3 times n plus 5. You can cancel out the 3's, and that gives you n plus 6 is greater than n plus 5, and you can subtract 5 from both sides. And then you have n is greater than n plus 1, which of course is true. Okay, so you want to get to the point where you get to something that is undeniably true. And so that way we can show that it is in fact decreasing. For the next one, we want to do something similar. So your first few terms are going to be 2 over 1, 3 over 2, 4 over 3. So it's not obvious what's happening. So you're starting with 2, and then you go to 3 halves, right? So is 2 bigger than 3 halves? Absolutely. You're going from 3 to 1.5. So sorry, this is 2. 1.5, this is 1.3, repeating. The next one would be 5 over 4, so that's 1.25. So it appears to be decreasing again. So we want to show that it's decreasing. So you want to compare your an, which is the n plus 1 over n, and we're going to try to say that it is bigger than n plus 1 over n plus 1. Okay, well, this is n plus 1 over n is possibly greater than n plus 2 over n plus 1. And so if we multiply here again by n times n plus 1, none of this changes our inequality sign because all of that's positive. You get n plus 1 squared being greater than n times n plus 2. Okay, well, this is n squared plus 2n plus 1, and this is n squared plus 2n. So if you subtract off n squared minus 2n from both sides, you get 1 is greater than 0, which is absolutely true. So we can say, yes, it is in fact decreasing. And then lastly, we have number 3. So an is 1 half to the n. And so if we think about our terms, that's 1/2, 1/4, 1/8, and that's clearly decreasing as your denominator gets larger. So let's look at y. So you are comparing 1/2 to the n. We're going to say is bigger than 1/2 to the n plus 1. And that's just 1/2 to the n greater than 1/2 to the n times 1/2, right? And so if you divide by 1/2 to the n, which we know is always positive, then you get 1 is greater than 1/2, which of course is true. And so therefore you can show that it's decreasing. Okay, so that's usually your strategy when you're looking at increasing versus decreasing. Oh, and there's one more. In this one, we're going to look at the same thing. So first couple terms. Now this one's alternating. So this is -1 to the 1 is -1/1. So we start out at -1. And then we're going to get a positive value. So you get n squared, which would be positive 4/2. So that's going to be 2. And when you plug in 3, you get -9/6, which is -1 and 1/2. And then when you plug in 4, you get 16/24, which is less than 1. So you can see that there is no pattern here because first of all, we're going to alternate back and forth, but you also start at 1 and then jump up to 2, and then it appears to be decreasing relatively quickly. So for all n greater than or equal to 1, this is not increasing or decreasing. It's doing a bit of both. It's increasing and decreasing. Okay, so some more things we want to comment on here. If a sequence is either increasing or decreasing, we say it is monotonic, right? So it's doing the same thing all the time. It's either always going up or it's always going down. That's the mono part. There's one thing happening. We can also talk about whether a sequence is bounded above or bounded below. And so that bounded above means that there is a number that you can choose such that all of your an values are less than that. Bounded below means that I can choose or identify a number for which your an's are always greater than that number. And if you can do both, then we say that it's bounded. And we get this nice little theorem here, the monotonic sequence theorem, that says every bounded monotonic sequence is convergent. Okay, so if it's increasing and it has an upper boundary, then it's never going to go above that upper boundary, so it's going to be convergent to that number or something smaller. The same thing if you think about the other direction. Okay, so we're trying to determine whether these 4 sequences converge by the monotonic sequence theorem. So we've got to be able to say multiple things. We've got to be able to say it's either increasing or it's decreasing, and that it's bounded. So this first one, let's take a look. Let's see. This is the same as n over e to the n. And if we think about some terms here, if you plug in 1, you get 1 over e. If you plug in 2, you get 2 over e squared, 3 over e cubed. Now keep in mind that e is 2 point something. And so it appears that these numbers are getting smaller because when you take 2 point something to these powers, they're going to go big very quickly. Okay, so this is likely decreasing. Let's see if we can show it. So we want to show that an is greater than an plus 1. And let's see what happens. So we have n e to the negative n, we're saying is greater than n plus 1 times e to the negative n plus 1, right? Which is n e to the negative n being greater than n plus 1 e to the negative n e to the negative 1. If we distribute, this is n e to the negative n e to the negative 1 plus e to the negative n, e to the negative 1. Now, if you divide through by e to the negative n, which we can do, this cancels, this cancels, this cancels. That tells us that this is n being greater than n times e to the negative 1 plus e to the negative 1. So this is n greater than n plus 1 times e to the negative 1, which is a little bit tricky. So in this case, let's see what happens next. So if we multiply by e on both sides, that moves my e over here. And I can divide through by n. So this is only true for, let's see, e greater than, if you divide that through, that's 1 plus 1 over n. And we have e minus 1 being greater than 1 over n. So that's only true for n greater than 1 over e minus 1. Now, e is 2 point something, 2.7, minus 1. So this is like 1 point something. So this number here is greater than 1. Sorry, is less than 1. So for all n greater than this number, which is less than 1, then n is greater than this value. Okay, our n are all greater than or equal to 1, which is greater than this number. So that checks out. So this is in fact decreasing. Now, it is decreasing, so I need to show that it is bounded below. Because if it's going down, I need to show that, hey, there's some bottom number that it doesn't cross. And that's not difficult in this particular situation because when you have n over e to the n, these are both going to be positive. So this has to be greater than 0, right? All e values are greater than 0, and your n's are greater than or equal to 1. So when you divide through, it's got to be greater than 0. So it is bounded below. It is also, if you want to bound it from above, this is going to be less than 1. And that's because n is always less than e to the n. So if you divide both sides by e to the n, then you end up with, right, and that's the case, it looks like something like this, right? So if you think about your graph, this is n, and your e to the n crosses up here and goes up. So our e is always above our n. So it's bounded in both directions. Right? It's always between 0 and 1. So that means it is bounded. And it's monotonic. In particular, we showed that it's decreasing, which implies that it is convergent by MST. Okay, so these are the types of questions that we're going to be working with. So there's a little bit of work to be done here when we're working with our sequences. Okay, let's take a look at this one. 2n minus 3 over 3n plus 4. Let's look at a few terms. So an is equal to, when you plug in 1, this is negative 2. So, nope, negative 1. Let's try that again. 2 minus 3 is negative 1. 3 plus 4 is 7. So we have negative 1/7. When you plug in 2, this becomes 1 over 10. And when you plug in 3, I get 6 minus 3 is 3. 6 times 3 is 18 plus 4 is 22. When we plug in 4, we get 5 over hold on, back the train up here. This isn't 22. Sorry about that. All right, that's my third term, so I'm plugging in 3. 9 plus 4 is 13. There we go. All right, and then 5. 15 plus 4 is 19. When we plug in 4, 1, 2, 3, 4, we're plugging in 5. That's 10 minus 3 is 7 over, let's see, I'm plugging in 5. Hold on. Cool, guys. It's important to keep track of this. All right, so my fourth term, when I plug in, 3 times 4 is 12, plus 4 is 16. And then I've got 19. There we go. Whew. Okay, so the question is what's happening here? Which one's bigger? Which one's smaller? So if I think about these two right here, I have 1/10 and 3 over 13. If I get common denominators, which would be 10, which would be 130. That means I'm multiplying the left one by 13 and the right one by 10. And so clearly this one is larger, okay? Which tracks because I've got negative 1/7. 1/10 is positive, so that one's larger. 3 over 13 is larger than that. Let's look at the 5 and the 7. So 5 over 16 and 7 over 19. Let's see. 5 times 19. Your denominator is whatever 16 times 19 is, which we don't really care about. But if you multiply the 5 times the 19, 5 times 20 would be 100. So this is 95. And if you multiply the 16 by the 7, you get 70 plus 42, which is 112, which is larger. So you can see it's getting larger each time. So what's happening here is this is increasing. So we're going to say this is increasing. Why? Well, if you take 2n minus 3 over 3n plus 4, we're going to say that that is less than when you plug in n plus 1. And then we've got to do some algebra to show this is true. So 2n minus 3 over 3n plus 4, we're saying is 2n plus 2 minus 3, and 3n plus 3 plus 4. And we're just going to multiply all this out. So this becomes 2n minus 3 over 3n plus 4. We're saying that's less than 2n minus 1 over 3n plus 7. So if we multiply to clear our denominators, so this is 3n plus 4 times 3n plus 7, and we're looking to see which is larger. So that's going to give us, sorry, I definitely did not give you guys enough room on these, and I apologize for that. Maybe what I'll do is add an extra page in here so I don't crowd myself too much. Okay. So from here, the 3n plus 4's cancel, and we have 2n minus 3 times 3n plus 7. And that's supposedly less than 2n minus 1 times 3n plus 4. So if we multiply all this out, we get 6n squared minus 9n plus 14n minus 21. And we're saying that that's less than 6n squared minus 3n plus 8n minus 4. So what can we do here? Let's see. This is the 6n squareds cancel out. You can subtract them off from both sides. And that leaves me with 5n minus 21 is less than 5n minus 4. You can cancel out your 5n's, and that's just saying that negative 21 is less than negative 4, which we know is true. Okay, so that tells us that our initial statement is correct. It is, in fact, an increasing function. Okay, so what else do we know? Now we've got to bound it. So we know that 2n minus 3 over 3n plus 4. We know it's increasing. So the smallest number that it could be, if I plug in 0 here, we know that this is going to be greater than or equal to negative 3 over 4, because we know it's getting bigger. So for my n equals 1, it's getting bigger as I go. So if I go one step before that to n equals 0, then I should be able to say that it is that this is true, okay? Then we want to bound it above, and we can bound it above by saying what number is bigger than this. Let's see. We guarantee that 1 is going to work here. Why is 1 going to work? If you have 2n minus 3 was less than or equal to if you multiply both sides by 3n plus 4. And that's true because if I subtract the n's, I have negative 3 is less than n plus 4. And that's always going to be true because n is a positive number, and when you add 4, that's much bigger than negative 3. So you can choose. These numbers don't have to be the ones that you use. You just have to be able to justify them. So now we can say that it is bounded and monotonic. Therefore, it is convergent. In fact, if we look at the limit, it's convergent to 2/3. Okay. So again, quite involved here as we're working our way through. Okay. All right, we did this one already. 1/2 to the n we already showed is decreasing. Okay. Now we know that this is exponential, so we know that 1/2 to the n has to be greater than or equal to 0. That's absolutely true because we have 1/2 two powers. Don't make it negative. And we know that this is going to be less than or equal to 1, right? And that's because if you have 1 over 2 to the n, we say is less than or equal to 1. Distribute your power. So 1 to the n is 1 over 2 to the n. And that says that 1 is less than 2 to the n. And for n greater than or equal to 1, so 0, if I make n 0, this becomes equal to 1. Sorry, I wrote that the wrong way. I went 1 less than or equal to 2 to the n. Right, which is what I want. So powers of 2 for n that are integers, as long as I'm above 0, because 0 will give me equal to 1, which is still true here. But then for all integers, as you take powers of 2, they get larger and larger. So that's always true. So you know that this is true, therefore it's bounded and monotonic, and therefore it's convergent. Okay. Okay. Here we go. N over n squared plus 1. Is this one we did above? I thought maybe it was. Nope, we didn't. Okay, so the first thing we need to do is show that this is either increasing or decreasing. So if we look at our terms, our an terms, if you plug in 1, that's 1 over 2. If you plug in 2, it's 2 over 5. If you plug in 3, that's 3 over 10. If you plug in 4, that's 4 over 17, 5 over 26. And you can see pretty quickly here that these are going to be decreasing. So we're looking for this to say it's decreasing. So we want to show that n over n squared plus 1 is greater than n plus 1 over n plus 1 squared plus 1. All right, so n over n squared plus 1. If we multiply this out, that's n squared plus 2n plus 2 when you add them together. Multiply this out, so times n squared plus 1 times n squared plus 2n plus 2. That's going to give you n times n squared plus 2n plus 2 greater than n plus 1 times n squared plus 1. This is n cubed plus 2n squared plus 2n. And we're saying that that's greater than n squared plus n cubed plus n squared plus n plus 1. And what you can see here is that an n cubed cancels. I can subtract an n squared minus n. And you end up with n squared plus n is greater than 1. And that's going to be true because n is greater than or equal to 1 and n squared is greater than or equal to 1. So when you add them together, they have to be greater than 1. So that's a true statement. So we know that it is decreasing, which means it's monotonic, and we just need to bound this. So n over n squared plus 1 is going to be greater than or equal to 0. Okay. It is also going to be less than, let's see, probably 1, right? So can we show that n is less than n squared plus 1? We probably can. N squared minus n plus 1. So you're saying that n squared minus n plus 1 is always bigger than 0. And that is likely true if we look at where it is equal to 0. That would be at 1 plus or minus the square root of 1 minus 4 over 2. And this is an imaginary number, so it doesn't have any places where it crosses 0. So that's also true. So we've got it bounded. And it's decreasing, so it's monotonic, which tells you that it converges. Okay, so in general, you're typically using, most of our boundaries here are going to be 0s and 1s. And then you've got to show that it's either increasing or decreasing. So there's a lot going on here.